Okay, so hi everyone. I'll be firstly, I'd like to thank all the organizers for arranging a really nice school in the last week, and then inviting me for the workshop and also school. I had a really good time. So today I'll be talking about since this is the workshop of big data and large cosmological surveys, I'll be talking about the outskirts of galaxy clusters, which we've been measuring using the dark energy survey, and which we've been essentially the splashback radius and how we can use it to understand some of basic questions. All right, so just starting at the beginning, we know that dark matter halos are essentially endpoints of structure formation. They're self-bound structures which have essentially the highest dark matter densities in the universe, and it's within the potential wells of these objects that the stars, galaxies, and everything that we know and love grow and evolve with time. So they've been studied quite extensively through simulations and actually also through observations. And largely, we understand that the distribution of dark matter inside these dense objects, from the simulation perspective, for a while, we knew that they follow something which is sort of very close to an NFW-like profile, where the inner regions tend to have a slope of -1, and as you move out to the outer regions of the cluster, the slope eventually rolls over to -3. While this has been widely studied and understood, the outskirts of the clusters had sort of received somewhat less attention. So for example, where we define the boundary of a halo to be, is there at all a boundary, has been sort of a question where you would get, sort of like a different answer depending on who you spoke to, right? So for example, ranging from, in general, the boundary of the halo is defined as the radius that would enclose some x times the background density. Typically, this is the virial overdensity, which comes from some physically motivated models of virialization of a cell-bound structure. Depending on which overdensity you choose, you could be scanning a wide range of different physical scales within the halo. And in fact, the halo is a dynamical growing thing, and different scales within the halo can be sensitive to different aspects of its evolution history. So one of the things that I've been studying is understanding is there a physical way of defining the boundary of the halo. And over the past few years, we've sort of come to understand that there is in fact a dynamical way of defining what region of space we want to call as being within the halo versus not belonging to it. So one intuitive way of looking at it is through the phase space of dark matter halos. And as soon as you look at the velocity, so this is the space of the radial velocity of the dark matter particles and distance from the center of the dark matter halo. As soon as you look at the space, you can clearly see that there are essentially two regions, one where you have multiple streams and one where you have a single infalling stream. This is, of course, an idealized case. And essentially, the boundary of these two regions is set by particles that are falling into the halo for the first time. So these are particles far away from it are expanding with the Hubble flow. Here is an infalling region with negative radial velocities. And so these are particles falling towards the center. They cross over smoothly. And as these particles in a growing potential reach sort of their first apocenter of their orbits, or are approaching the first apocenter of their orbits, they essentially chalk out two distinct regions separating this orbiting region from the infall region. So essentially, the surface of these particles approaching apocenter is essentially what separates out the inner multi-streaming region of the halo from the outer infalling region. For an idealized spherical case, you get those beautiful cold streams. If you had And in that case, if you essentially from the phase space, you went to the density profile, integrating along the velocity direction, at every apocenter, in fact, you would get these caustics. So these are for a self-similar initial density, which has been studied by Bertschinger, Fillmore, Goldreich, and by many people over the years. And you'd get these beautiful caustics in the density profile. Of course, in a more realistic situation, even if you introduce some amount of ellipticity, you wash out these caustics throughout the surface. But the outermost caustic, or the outermost jump in the phase space distribution still imprints itself on the dark matter distribution. So this was first pointed out by Diemer and Kravtsov in around 2014, where they found that even in simulations, if you stack over a wide range of halos at a similar mass, if you stack over a large number of halos at a similar mass, you see that the density profile of the halo steepens over a narrow range. And so this is a stacked density profile on the top panel and the logarithmic slope on the bottom panel. So the slope of the density profile essentially becomes very steep near the edge, somewhere near the virial radius. And it can become much steeper than NFW, which is this dot dashed line, and approaching even -4 or even greater than that in some cases. So essentially, this is telling us that the halo, the one halo term essentially has a sharp cutoff somewhere. And that cutoff is tracing this phase space boundary. So when you look at the stacked phase space boundary of halos in simulations, you then see a steepening at the boundary. And if you chose particles that have low radial velocities, you would actually bring out the feature even more. So the location of the minimum is what we in practice call the splashback radius. The location of this feature is sensitive naturally. It was found to be sensitive, very sensitive, firstly to the mass of the halo, determining what the size of the object is, and then also on secondary properties like how quickly the halo potential is growing. So how far out you can go in each orbit depends on how much the potential has grown. So if you have a fast accreting halo in units of r over r200, you would have a smaller boundary than if you were a slowly accreting halo. Similarly, the overdensity at splashback is the overdensity at this radius also depends on how quickly the background universe is expanding. So it also depends on the redshift at which you're observing the object. So this is right. So the other thing that will be relevant in the introduction is, of course, that this boundary of a halo is the splashback radius imprints itself in all the collisionless components of that make up a dark matter halo. The subhalos within these objects also, if you looked at the subhalo density distribution, you would also see a sharp boundary corresponding to the minimum of the logarithmic slope profile in its density distribution. Of course, subhalos are not point-like particles like we imagine the dark matter particles to be. They are extended objects, and particularly for massive subhalos that are prone to dynamical friction, you can see a shift in the location of the splashback radius compared to the particle splashback radius in halos. So this provides essentially a dynamical way of defining where the boundary of the halo is. In the simulation space, there's been a lot of work to actually understand if we can find these surfaces in simulations using particle apocenters or using solid angles where we can go in different directions to see where the density fall off is. And there's a large amount of literature that have been really trying to define these halos in simulations and look at how we reconsider how we think of mass or collapsed mass, and re-answering, re-looking at some of the standard things that we look at, like the universality of the mass function and so on. So why do we care about the splashback radius, why it may be of interest. Of course, as I was saying, it forms a physical boundary of the halo. It gives a physical definition of halo mass, or mass bound to, or mass that is collapsed within the potential. It separates the virialized and falling region. It's also sort of like a fundamental length scale. If you have a dark matter structure around you, you should find a feature at the edge. And it's made up of the most recently accreted material, so which has not necessarily been phase mixed with the rest of the object. So the physics of its is quite simple to understand, and we can use it to probe other things. And one of the things that has been most exciting to me is that it is accessible observationally, and we can go out and actually measure it. Just to step back a little bit, we're used to thinking of halos as simple NFW-like structures, which is true on average. But halos are, of course, dynamical objects. Their mass accretion history depends on the environments in which they have evolved. And we can really trying to sort of unraveling the halo layer by layer, we can really try to understand the different aspects of its evolution and use it for other things. So one of the studies that we've been doing is sort of to understand the mapping from the initial conditions to the final halo profiles, going through the mass accretion histories of the halo. And in the study with Louisa Lucy Smith, who's now a postdoc at Max Planck, and Risa Wexler, we were basically looking at trying to feed in the initial conditions and the mass accretion histories of halos into a machine learning framework to predict the mass at different radius of the final halo. And one of the things that we found, particularly for the mass accretion history, some of the IC information is obviously naturally incorporated in the mass accretion history itself. We found that essentially the dark matter density profile at the final redshift, there are essentially 3 timescales that really stand out in the halo's accretion history. Particularly a timescale that corresponds to matter that has fallen in at about at sort of several dynamical times ago, a timescale that corresponds to matter that is freshly falling in its first infall, and a very recent timescale where the things that are merging into the halo have still not been disrupted. So machine learning, basically gave us these 3 timescales. But if you actually went and looked at in retrospect, when we went and actually looked at the halo particle time distributions, we saw these 3 timescales standing out quite clearly. So if you look at the halo particles in different radial shells from the center of the halo, you see that you plot the distribution of the time at which they were accreted onto the halo. You can see clearly these 3 distinct timescales. At the outer radii, you particularly see these 3 timescales, and at the inner radii, you see these 2 timescales. So the first later peak, or the more recent peak, corresponds to essentially material that is infalling into the halo for the first time, and it's dynamically separated from rest of the virialized matter. And at different radii, most of the matter that we think of as virialized or haven't been inside the halo will have been accreted at the age of the halo you can think of is slightly different at different radii. So in any case, I wanted to show this because it's nice to think of the halo not as this, it's nice to think of the halo as being formed of these different parts that have essentially been brought together at different time. And in principle, we could try to back out that information from observations. So in the second half of my talk, I'll basically talk about the observations of dark matter halos, and particularly focusing on splashback radius and the outskirts. So of course, we've heard in the morning, and we'll hear again, that we can observe dark matter halos in many different frequencies. Typically, in the work that I've been doing, I've mostly been studying the dark matter distribution, either using the distribution of other galaxies around it, So trying to map out the potential using the number density of galaxies, or using weak lensing. So so measuring the mass directly using a weak lensing signal. So particularly we are focusing on galaxy clusters because these are the most massive objects that essentially dominate their environment, and we expect to see their splashback radius clearly because it's sort of not buried inside one can think of as the 2 halo term, or it's not in the neighborhood of other massive things. Right, so typically we measure using the galaxy number density distribution or the lensing, and what we do is essentially we measure the 2D projected galaxy distribution or the weak lensing signal and model it using the Diemer-Kravtsov profile, which is essentially a density profile that has an inner collapsed and an infall part and a transition part that essentially captures this transition from the collapse to the infall through this F trans term. So the first observational results for the measurement of the splashback radius was done by Surhud and Hiranau here using red mapper optical clusters in the SDSS survey. And it was later followed up by the DS survey using optical clusters. And just to give a little bit of a history for the optical cluster samples, it was found that the location of this, so on the bottom panel are the measurements. So the pink curve is essentially the lensing measurement of the slope of the density profile, and the black curve is the slope of the density profile measured from galaxy number density distribution. And there was a 20% discrepancy in the location of the minimum when it was compared to simulations. But over time, we've learned that we need to sort out a lot of systematic effects in optical clusters, like projection and understanding the richness-mass relationship better. So one of the other things that we did is we went and looked at clusters selected using the SZ signal instead of optical clusters. And we used both the SPT survey and Zurcher and Moore here use the Planck survey. So we made measurements of SPT clusters across the DES galaxies. So the distribution of DES galaxies around these SPT clusters in its footprint. And these are HSC galaxies across the Planck clusters. And when we look at these SZ clusters, essentially we find that the location of the minimum is quite consistent with what we expect from lambda CDM. At least there is no significant difference. More recently, we've been studying galaxy clusters from the ACT survey. Now we have much larger overlap, much larger sample of SZ selected clusters from ACT. So we have about 1,000 clusters from the ACT survey, and we are measuring the galaxy density distribution of the DS galaxies around these 1,000 ACT clusters that range from 0.15 to 0.7. And essentially, we measured not only the cluster cross galaxy number density distribution, but we also measured the lensing around these clusters. And as you can see here, these are the fits to the model that we are plotting, and these are the 3D slope profiles. And as you can see that firstly, we found that galaxies and dark matter follow each other, which was nice to see directly in data. And the location of the minimum generally coincides in the lensing and the galaxy measurement. So essentially there is, and when comparing to lambda CDM simulations, we find that they're very consistent with where we expect splashback to be. There was also recent work by Dhaya and Vejagane and Chiwe, where they measure the SZ profile itself and compare it to the dark matter distribution. And essentially they find that the location for the dip in the gas profile is also consistent with the dip in the dark matter profile. There's also been recent work using the EFEDS cluster that we heard about this morning by Divya Rana and Surhud, where they've made the first measurements of splashback using the X-ray galaxy clusters. And currently we have this, this large array of measurements, and essentially this is our expected relationship from lambda CDM. And we, apart from a few measurements, I think we are essentially quite consistent within sigma with lambda CDM so far. All right, so now that we have these measurements in the last 5 minutes, as Hamza tells me, I'll quickly go through with what can we do with by measuring splashback. So one of the things that we've been looking into is how does this feature change if we look at different tracers of the potential, say blue, red, and green galaxies. So one of the things that we found is when we look at the distribution of red galaxies around clusters, we see this sharp dip in the outskirts, whereas when we look at blue galaxies or green galaxies, we essentially see that the minimum of the slope is either shifted to a very much lower radius, or essentially we don't see a splashback-like feature. So essentially what could be going on, a simple toy picture that could explain what we are observing is essentially that if galaxies, unlike dark matter, are not static things, they change if there are environmental processes inside the cluster that end up basically changing the star formation properties of a galaxy, then that would, and they're sensitive to intercluster processes, so therefore they would be sensitive to the orbits on which they are. So if you had a population of blue, green, and red galaxies falling in, as the blue galaxy fell in, if it does not remain blue post pericenter, it's essentially never going to reach splashback as a blue galaxy, right? So essentially, if it gets quenched before it reaches the first apocenter, you wouldn't see the transition, the phase space boundary at the location of a splashback, but at a shifted position. If it just died out at pericenter, you wouldn't see splashback at all. And if it crossed pericenter, you would essentially see the multi-streaming to the single stream boundary somewhere a smaller radius. So using this picture, we looked at, we essentially tried to map the time in which a galaxy falls in to the location of where the minimum of the slope is, essentially trying to see that how long blue galaxies, red galaxies, and green galaxies on average have been inside clusters. Adding to that, we also fit a simple quenching model to essentially get to what kind of quenching what models of quenching we would require, or how can we basically constrain a quenching model given the galaxy distribution of these 3 different colors inside of the clusters. Of course, so we had some first constraints. We saw that there has to be a delay time of about 1 gigayear and an exponential quenching time of 0.6 gigayears. Of course, the model is quite simplistic. We did not consider angular momentum of orbit, and when we went and looked into hydrosim, the picture can be quite dramatically different. But I think really using both the slope and the density distribution together, we can really start to understand the history of the infalling galaxies in the clusters. All right. So finally, I won't go into the SIDM. I guess looking at the future, I'll just, one of the things that I've been interested in doing is just like galaxy clusters. And using the full density distribution, we can really know about the evolution of the things that have been inside the cluster and the cluster as a whole. One thing that I, looking forward, want to do is, can we go and measure the splashback radius in lower mass halos? Can we measure this transition, the outskirts of the density distribution dark matter halos in Milky Way mass and group mass halos, or even going down to dwarf mass halos? It's harder to do that because these halos are typically in the environments of around other halos, essentially, and their infall transition, that break in the profile, is really buried inside the 2 halo term. But one way to go and look for it is to essentially look at low mass galaxies in different environments. And you can see that on the left-hand panel, you can see the density distribution of low mass galaxies split on the overdensity at 10 megaparsec. And as you go to lower density environments, you really start to clear out this transition region. And essentially, you can get pretty sharp splashback features when splashback, or you can really map out the outskirts well when you go into these low density environments. So I'll stop over here, and I'll say that essentially, we have a way to understand the evolution of dark matter halos with this picture of really also understanding the outskirts really well. I've only spoken about in spatial coordinates. In velocity space, there's a lot of work being done by Hanong, Eduardo Rosso and group. And you should definitely also go and look at that. And yeah, I think in the future with much larger cluster samples, much deeper surveys, we'll really be able to map out the inner halo of a wide range of objects. Okay, thank you.
Thanks a lot, Susmita.